In this class, you will learn basic things about the OSI reference model and basic aspects of the OSI model. Upon completion, you will be able to understand the architecture of the OSI model. The OSI model is a conceptual framework that helps standardize how computer networking protocols should work with each other, and it really helps aid your understanding as you are learning about networking as well. As said, it is a conceptual framework. It is not a physical thing or an actual protocol. Actually, this is going to form a bedrock of your understanding of networking, so it is a really important section. We will also go into the definitions of the different layers that make up the OSI model. We will also cover the TCP/IP suite and discuss how it relates to the different layers of the OSI model. Let's get started. The International Standards Organization, or ISO, is a multinational body dedicated to worldwide agreement on international standards. It was established in 1947. An ISO standard that covers all aspects of network communications is the Open Systems Interconnection, or OSI model. It was first introduced in the late 1970s. Please note that ISO is an organization and OSI is a model. The OSI model suite is made of 7 layers: physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and application layer. The first 4 layers provide physical standard, network interface, internetworking, and transport functions. The 3 topmost layers in the OSI model provide applications, coding, encoding, building, maintaining, and terminating the session. Now, you must be thinking, the OSI model representation starts from top to bottom, from application to physical layer. However, according to the OSI model, the physical layer is the layer 1, and the application layer is layer 7. The data representation, coding, encoding, and encapsulation happen from top to bottom, and data decapsulation, decoding, and representation happen from bottom to top. Let's see, this is my laptop and this is my web server. They are connected to a switch in the same LAN network. Now the point is, how do they communicate with each other and exchange data? Also, which model do they refer to communicate? In general, in day-to-day activity, you browse websites and download media like file, movies, songs, and software. However, did you get a chance to know exactly how it works? So, if I am trying to browse websites and download something from there, the OSI layer takes care of end-to-end communication. Either it is from client to server or server to client. Now, according to the OSI model, the request data to browse the website will be managed by the layer 7, or application layer. Now application layer makes the appropriate changes and hand over the data to presentation layer, or layer 6. In the next stage, the presentation layer receives the upper layer data and makes the appropriate changes. Post making the appropriate changes, now the presentation layer hand over the data to session layer, or layer 5. At this stage, my data is successfully received at session layer, or layer 5. Similarly, the session layer makes the appropriate changes in data received from the upper layer. Also, it passes the data to transport layer, or layer 4. Layers 5, layer 6, and layer 7 are known as the upper layers, and they are more important for application developers rather than network engineers. Network engineers start to get really interested when we get down to layer 4. So we have got our upper layer traffic, or data composed, that then gets encapsulated with our layer 4 header, which is the transport layer. As soon as data comes on layer 4, traffic is going to be either TCP or UDP, and it will include the port number, such as port 80, if it is web traffic as our example. Now, if you don't already know the details of TCP, UDP, and port numbers, don't worry about it. We're going to cover all of this information in much greater detail in the later lessons, and actually, throughout the entire course. The next thing will happen is that the upper layer data will then be encapsulated with our layer 3 header. Layer 3 is the network layer, and important information that is included there is the source and destination IP address. A network device that operates layer 3 is our routers. The next thing that will happen as we compose our packet is the sender will then encapsulate that information in the layer 2 header. Layer 2 is the data link layer, and important information there is the MAC address if we are sending this over an Ethernet network. The network device that works at layer 2 is our switches. Finally, this packet is now ready so that we can actually transmit it over the wire. When we do that, we are down to layer 1, which is the physical layer. So, we have now compassed a packet at the sender side. We have put it onto the wire. It is going to travel over the network in a form of binary, and it's going to reach our receiver. The order of operations is going to be reversed now because it comes in at the physical layer. The receiver will process the packet from the bottom layer to the top layer now. So, it comes in at the physical layer. The receiver will then look at the outside header, which is the layer 2 header, and it will check that this frame is for it. It will check the destination MAC address in the layer 2 header. If it is not for it, it will just discard the frame. If it is for it, then it forwards the packet to the upper layer, which is the network layer. Now, it will continue with de-encapsulation. It will then look at the layer 3 header. It will check the destination IP address, and again, it will check that the packet is for it. If not, it will discard the packet. Then we carry on with our de-encapsulation on the receiver. It will look at the layer 4 header. What this is useful for is, imagine the receiver is not just a web server listening on port 80 web traffic. Let's say it is also an email server as well, listening on port 23 for email traffic. Well, how does it know if this traffic is for its web server application or its email server application? It can tell by looking at the port number of the application. Next, we will carry on with the de-encapsulation. We'll strip off the layer 4 header. What this is useful for is, imagine the receiver is not just a web server listening on port 80 web traffic. Let's say it is also an email server as well, listening on port 25 for email traffic. Well, how does it know if this traffic is for its web server application or its email server application? It can tell by looking at the port number of the application. Next, we will carry on with the de-encapsulation. We'll strip off the layer 4 header. We will look at the layer 5 header at the session layer. We will carry on up. We will then look at the layer 6 header and then the layer 7 header. So, that is the whole thing. That is how we got traffic from the sender to the receiver as far as the OSI model was concerned. Looking at the benefits we get from the OSI model, engineers do not need to design a technology to work end-to-end from top to bottom of the model. They can just focus on their layer of expertise and make sure that they comply with the standards for the layers above and below. This leads to open standards on multi-vendor interoperability. For example, if you are an application developer, you can just focus on the top 3 layers. The lower layers are the domain of network engineers. So, you do not need to understand them. You just need to make sure to focus on your part and comply with the OSI standard. Troubleshooting is also easier because you can analyze a problem in a logical fashion, layer by layer. As you become more experienced with networking, you will think according to the OSI model when you are troubleshooting or learning a new network technology. For example, if you are troubleshooting a problem without having OSI model information, and you start looking at the problem in a complicated way. You are working on routers and switches or etc., but didn't find the issue. And suddenly from the other end, your customer says, the issue is because the cable was unplugged. Having knowledge of each aspect of the OSI model is very important. Otherwise, it will be very hard to survive in the network field. Initially, it is very hard to remember the OSI layer. I will solve this problem for you. There is a classic acronym that you may remember to understand the OSI layer. Please do not throw sausage pizza away. Let me again tell the OSI layer's name here. The layers are physical layer, data link layer, then network layer, then transport layer, session layer, presentation layer, and application layer. The Internet Protocol was originally developed by the Department of Defense, and it was a cornerstone for a group of protocols that became known as the TCP/IP protocol suite. The DoD developed their own networking model, which became known as the TCP/IP model. Without the framework that network models provide, all network hardware and software would have been proprietary. Organizations would have been locked into a single vendor's equipment, and global networks like the internet would have been impractical, if not impossible. The two most recognized network reference models are the Open Systems Interconnection, or OSI model, the Department of Defense, or DoD model. Protocols on one layer will interact with protocols on the layer above and below it, forming a protocol suite, or stack. The TCP/IP suite is the most prevalent protocol suite and is the foundation of the Internet. A network model is not a physical entity, and there is no OSI device in the market. Manufacturers do not always strictly adhere to a reference model's blueprint, and thus not every protocol fits perfectly within a single layer. Some protocols can function across multiple layers. The TCP/IP protocol suite is made of 5 layers: physical, data link, network, transport, and application layer. The first 4 layers provide physical standards, network interface, internetworking, and transport functions that correspond to the first 4 layers of the OSI model. The 3 topmost layers in the OSI model, however, are represented in TCP/IP by a single layer, called the application layer. The consolidated DoD model is generally regarded as more practical than the OSI model. Upper layer protocols often provide services that span the top 3 layers. A converged data link and physical layer is also sensible, as many technologies provide specifications for both layers, such as Ethernet. The diagram displays where common protocols fit into the DoD model.